Hi everyone, myself Dr. Ashok Babu. So in this video, I am going to discuss about the inductors and inductances. First, we'll define what is an inductor, and then we'll define inductance. So let us assume a circuit. So here, please go through the circuit diagram. So here, let us assume there is some windings are there. So a circuit are a closed conducting path carrying a current I. So let us assume a closed circuit is there. So for this closed circuit, apply a current. So due to the application of some current, here we can generate a magnetic field due to the process of induction. Due to the process of induction, here a magnetic field is induced in the coil. So here, due to the magnetic field, a flux psi can be induced in the circuit diagram. So here, let us assume the flux induced in the magnetic field is psi is equal to integral B into ds. Integral B into ds. And assume that the circuit is having n identical turns. Let us assume the circuit is having n identical turns. If the circuit is having n identical turns, then the flux linkage, let us assume the flux linkage is lambda. The flux linkage lambda is equal to number of turns n into the flux linkage. So let us assume, if we assume the number of turns in a circuit are n, then the flux linkage lambda is equal to number of turns n into the flux linkage psi. Flux linkage psi. So therefore, if the medium surrounding the circuit is linear, the flux linkage lambda is proportional to the current applied in the circuit diagram. Therefore, the lambda is directly proportional to current I. Therefore, we can express it as lambda is equal to L into I, where L is some proportionality constant. And L is also known as the inductance of the circuit, where L is a constant of proportionality called the inductance of the circuit. So here, a circuit or a part of the circuit that has inductance is called the inductor. I repeat once again, a circuit or a part of the circuit, that has the inductance is called the inductor. So here we may define the inductance L of an inductor as the ratio of the magnetic. Already we know that lambda, the flux linkage lambda is equal to L into I. Therefore, from this equation we can define inductance L is equal to the ratio of flux linkage to the passage of current applied, the ratio of flux linkage to the current applied or current passing through the inductor. Therefore, L is equal to lambda by I. But we know that lambda, the flux linkage lambda is equal to N into psi, where N is the number of turns, psi is the flux in the circuit diagram. Therefore, N psi by I. The unit of inductance is here Henrys, which is the same as Weber per meter. So here the magnetic energy, we can calculate the magnetic energy by using the energy stored in a inductor. So similarly, in electric field, we can calculate the energy stored in the electric energy stored using a capacitor. There, the energy stored equal to half CV square. Same as the electric field, in magnetic field, in magnetic field also, we can calculate the energy stored. The energy stored due to the inductor here. Therefore, the energy stored, the magnetic energy stored, Wm is equal to half Li square. So from this equation, we can find out the inductance as, so it is Li square is equal to, or it is Li square is equal to, just we cross multiply the equation, 2 into the energy stored in magnetic field, and therefore the inductance L is equal to 2 into the energy stored in magnetic field by I square. L is equal to 2 Wm by I square, which is the inductor or inductance of a circuit diagram. Next, so we can calculate the self-inductance. After defining the inductance, we will see the self-inductance. What is the self-inductance? How we can generate the self-inductance? The self-inductance of the circuit may be defined or calculated from the energy considerations. So here, if instead of having a single circuit, here we will use the two circuit diagrams. We have to use two circuit diagrams, and the two circuit diagrams carrying the currents of I1 and I2 as shown in figure. So here a magnetic interaction exists between the two circuits. That is nothing but, so due to the induction, due to the process of induction, suppose current I1 is there, current I2 is there. So this is the first circuit, this is the second circuit. So here due to the process of induction, let us assume a current I1 is applied to the circuit diagram. So due to the application of current, here the magnetic field is induced. Due to the process of induction, the magnetic field is induced. And due to the magnetic field, we have the flux in the circuit diagram. So here, due to the passage of I1, here we have the inductance, you have the fluxes. So here flux psi11 is there, flux psi22 is there. These two are known as the self fluxes. And here we have psi12 is there, psi21 is there. So these two are known as the mutual fluxes. So the flux in one due to the second circuit, the flux in two due to the second circuit. So it is a self inductance in the circuit one. It is a self inductance, self flux in the first circuit diagram. This is a self flux in the second circuit diagram. So there are the 4 fluxes available in the circuit. So here there are 4 important fluxes: psi11, psi12, psi21, and psi22 are the 4 fluxes. So apart from these 4 fluxes, psi11, psi12 and psi11 are the fluxes in circuit diagram 1 due to the current I2. Similarly, psi21 and psi22 are the fluxes in circuit 2 due to the circuit 1. Next. So if let us assume B2, where B2 is the magnetic field flux density, in circuit 2. Let us assume the magnetic flux density B2 in the field due to the current I2. And S1 is the area of the circuit 1. Then here we can define the flux psi12, the flux in 1 due to the circuit 2. Psi12 is equal to integral surface area S1 into B2 into ds. Similarly, here we can define the mutual inductance Mi2. As the ratio of flux linkage. Lambda 12 is equal to N1 psi12 to the on the circuit 1 to current I2. So here we can define the mutual inductance as M is equal to the flux linkage to the current. Therefore, here Mi2 is the flux in 1, mutual flux in 1 due to the circuit 2. So it can be defined as it is equal to the flux linkage in circuit 1 due to the circuit 2 by the current flowing through the circuit 2. Therefore, which is equal to lambda 12. The flux linkage in 1 due to the circuit 2 can be defined as N1 into psi12 by I2. Similarly, we can define the mutual inductance M21. It is the mutual inductance in circuit 2 due to the circuit 1. M21 is equal to lambda 21 by I1, which is equal to lambda 2 can be defined as N2 into N2 is the number of turns into self flux by I1. So here generally mutual inductance, it can be shown that the energy concept, that is the medium surrounding in the circuit is linear. If the medium surrounding the two circuits are linear, then we can write M12 is equal to M21. It means the two mutual inductances are similar. If the circuit surrounding the circuits are linear, then we can define two mutual inductances are equal. M12 is equal to M21. Therefore, here we define the self-inductance of the circuits 1 and 2 respectively as self-inductance L1 is equal to lambda 11 by I. Actually, we know the relation L is equal to inductance equal to flux linkage to the current. It is the ratio of flux linkage to the current. In a similar fashion, we can define the L1. L1 equal to lambda 11 by I1. But lambda 11 is a flux linkage. Therefore, here you can write N1 into psi1 by I1. Similarly, we can define the L2. L2 is equal to lambda 22 by I2, which is equal to N2 into psi2 by I2. So here psi1 and psi2 are the fluxes. So where psi1 is equal to psi11 plus psi12. Psi2 is equal to psi21 plus psi22. The total energy in the magnetic field is the sum of the energies due to L1, L2 and mutual inductances M12 or M21. Therefore, we can define the total energy stored in an inductor is Wm is equal to W1 plus W2 plus W12. Where W12 is the energy stored due to the mutual inductance. Therefore, here we can express W1 as half Li square, half L1 I1 square plus half L2 I2 square plus or minus mu I12 into I1 I2. Now, so an inductor is a conductor. An inductor can also act as a conductor arranged in a shape appropriate to store the magnetic energy. where capacitor is used to store the electric energy and inductor is used to store the magnetic energy. So here the typical examples of inductors are toroid, solenoid and coaxial transmission lines and parallel wire transmission lines. These are the examples of inductors. So an inductor as coaxial or parallel wire transmission line. The inductance produced by the flux internal to the conductor is called the internal inductance. So I repeat once again, the inductance produced by the flux internal to the conductor is called the internal inductance LIN, while that produced by the flux external to it is called external inductance L external. Therefore, the total inductance equal to internal inductance plus external inductance. So this is about the inductance and inductors and inductances. So now we'll discuss about the small topic, magnetic energy. So here to discuss about the magnetic energy, so let us assume a rectangular coordinate system. In rectangular coordinate system, assume a differential volume. Assume a differential volume placed along the xz plane and the current is flowing along the y direction. So here due to the flow of current along the y direction, the magnetic field flows along the y direction. So in other two directions, we don't have the magnetic field. So because the current flows along the y direction, we have the magnetic field. So just as a potential energy or electrostatic energy, so here we can define the magnetic energy. So here electrostatic energy can be defined as W is equal to half dE, where D is the electric flux density, E is the electric field intensity, is equal to half into epsilon E square into dV. Similarly, in a similar fashion, we can define the magnetic energy. Wm is equal to half Li square, where L is the inductance, I is the current flowing through a circuit diagram. So here the energy is stored in the magnetic field B of the inductor. So here consider to find out the energy stored in a inductor or the magnetic energy stored. So here you let us assume a differential volume. Consider a differential volume in a magnetic field. So let the volume be covered with the conducting sheets at the top and bottom surfaces of the of a differential volume with current delta I. Repeat once again. Let the volume be covered with conducting sheets at the top and bottom surfaces with the current delta I. Assume that the whole region is filled with such a differential volumes. Then we can define the inductance. Here we can define the inductance as L is the ratio of flux to the current. L is the ratio of L is equal to psi by I. Therefore, if you assume the change in inductance equal to change in flux to the change in current. Change in flux to the change in current. Therefore, so here the change in flux can be defined as it is mu h into delta x into delta z, because so here the flux flowing through the because of current flowing through the current is flowing through the y-axis. So due to the passage of current along the y-axis, here we have the magnetic field along the y direction. So here we can find out the delta psi as, so just see here. So here we know that the flux psi is equal to closed integral B into ds. You differentiate the equation on both sides. Therefore, d psi is equal to B into ds, or so d psi in place of B into d psi. Here we can assume differential change or change in flux equal to change in magnetic field into delta S, or we can write directly B into change in surface area, but B is equal to, we know that mu h. Therefore, change in flux is equal to, it is mu h into change in surface area. Delta psi is equal to mu h into delta S. So here delta S is a surface area. So here because the current is flowing along the y direction, for the surface area we need to assume the delta x and delta z only. Therefore, delta in place of delta S you substitute, it is mu h into delta x into delta z. Therefore, delta psi is equal to, you substitute mu h into delta x into delta z. Delta psi is equal to mu h into delta x into delta z by delta I. So here we can find the current, because the current is flowing along the only y direction. Therefore, the current delta I is equal to magnetic field intensity into delta Y. Magnetic field intensity into delta Y. If we divide the equations, two equations, equation 2 and equation 1, then here we can, if you substitute equation 2 in equation 1, not divide, if you substitute equation 2 in equation 1, therefore here it is, the change in the stored magnetic energy is equal to half Li square. We have the formula half Li square. So here in place of L, here I am assuming change in L into change in I square. Change in L is equal to, already we know that change in L is nothing but mu h delta x delta z by delta I. So delta I cancel each other. We have only one delta I. So in place of one delta I, you can substitute h into delta y. Therefore, is equal to mu h is equal to, therefore mu h into delta x into delta z into h into delta y. Therefore, it becomes mu h square into delta x into delta y into delta z. So delta x, delta y, delta z is the change in volume. Therefore, we can write it is half is already there. Half mu h square into change in volume. Half mu h square into change in volume. So here the magnetostatic energy density can be defined as, it is Wm is equal to change in stored energy by change in volume. Change in stored energy by change in volume. Therefore, it is half mu h square. So if you bring delta change in volume to the denominator part, so it becomes the magnetostatic energy, stored magnetostatic energy density, so which is equal to half mu h square. So here hence the Wm, the stored magnetic energy, is equal to half mu h square, which is equal to half Bh, because B is equal to, we know that mu into h, B is equal to, we know that B in mu h, so it is equal to half Bh, and we know that h is equal to, we can write B by mu. Therefore, if you substitute h equal to B by mu, therefore it is B square by 2 mu. B square by 2 mu. So this is thus the energy stored in a magnetostatic field in a linear medium is W is equal to integral Wm into dV. Therefore, it is W is equal to half into integral B into h into dV, or which is equal to half into integral mu h square, or which is equal to half into B square by mu. Half into integral B square by mu into dV. So in three ways we can find out the energy stored in a magnetic field. So this is about the inductor, inductance, and the magnetic energy stored. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.